Hello, my name is Bing and I am from Tribeca Hills High School. My project is Increasing Propeller Performance, investigating the optimization and potential of a novel propeller concept through computational fluid simulation, experimental testing rig, and commercial drone integration. First, tip vortices are areas of turbulent flow that reduce propeller efficiency and increase noise. This is one of the key limitations of traditional propellers. As seen in the bottom picture, toroidal propellers feature a closed-loop design and mitigate tip vortices. Only surface-level comparison of toroidal versus traditional propeller designs have been conducted, and this project aims to dive deeper into the optimization and performance of toroidal propellers. This is a diagram from my project journey. I started with 9 different propeller configurations, and the simulation and testing were conducted on. The initial simulation test setup and the test stand were generated inaccurate data, and I had to redesign them. With the redesigned simulation and test stand, I got accurate data and was able to perform mathematical calculations to get important numbers, such as efficiency. The same thing happened with the integration and flight of my personal drone. It required a redesign to fly well. The performance data from the simulation, experiments, and drone flights were analyzed, and conclusions were reached. My initial simulation setup featured the air rotating around a static propeller, called global rotational. My initial test stand featured a propeller on a cart that was pushed into a load cell, and my initial toroidal propellers on my personal drone were fabricated using fused deposition modeling. The equations used to calculate the various performance numbers from my simulation and experimental results are also shown here. My final test stand features a propeller rotating an arm into a scale. The simulation is now local rotational, where the propeller is rotated around the static air, and the prototype propellers on the drone are fabricated using multi-jet fusion. Here are my results. We will analyze them in the following slide. From our results, we can claim that the wider toroidal configurations have a greater efficiency and decreased noise compared to the traditional and narrow toroidal configurations. We can also see that the MJF fabricated propellers have a significantly higher efficiency and less noise than the FDM fabricated configurations. We can also see that the toroidal propellers have their own limitations as well, in the form of increased mass that decrease motor response, leading to aircraft instability. We can conclude that both loop width and fabrication method drastically affect propeller performance, as well as and verify that toroidal propellers can outperform traditional propellers when optimized. Some of the impacts of this project are that this is the first comprehensive study of the aerodynamics of both traditional and toroidal propeller configurations, as well as the first in verifying a new hybrid toroidal propeller design. Also, this project provided the first insight to the limitations of toroidals in terms of delayed motor response. Thank you.